And you will see we have total, in terms of the hyperactivity and inattentiveness scale, this is baseline versus week 8. And we have numbers for placebo and for St. John's wort. And what we see is we see the baseline score for the placebo group was 25.9, and at the end of week 8 the score was 20.7, so there was a difference of negative 5.2. Okay, and for those who took St. John's wort, the baseline score was 27.6, and at the end of week 8 it was 23.22 for a difference of 4.4. Okay, if you create a confidence interval around this number, negative 5.2, and around negative 4.4, you get negative 9.4 to negative 1.1. Let me just zoom in a tiny bit more. And so this indicates there's no 0 within this interval. So that indicates we have evidence that there is a difference between baseline and week 8. Okay, so there's no 0 in this interval. So we have evidence that there's a difference between baseline and week 8. Same thing for the St. John's wort group. There is no 0. 0 is not within the interval. So we have evidence that there is a difference between baseline and week 8. Okay. But if we look at the numbers themselves, negative 4.4 versus negative 5.2, are these two numbers significantly different? The p-value is 0.76, so these two numbers are not significantly different from each other. Okay, and so this means the difference between placebo and St. John's wort is not significant according to this study. So we're definitely seeing improvement in ADHD or hyperactivity and inattentiveness. We're seeing improvement in these scores, but if we compare them to each other, we don't see a difference. So I think at the beginning in the abstract, it says for treatment, basically it said no difference between groups. Okay, I can't read this. But basically there's not a significant difference between the placebo and the St. John's wort group, okay, in terms of the effect. But we're seeing a placebo effect in that those who took placebo saw improvement, and those who took St. John's wort also saw improvement. Okay. All right, and so you have all of that. When you have also this thing, which talks about baseline characteristics of study participants, okay, and they go through all of this stuff just to see if just to make sure that the two groups are somewhat similar looking, okay, and that at the end of the study you don't want somebody to say, oh, the reason why the scores were different was because this group had more whatever, these type of people, and this group did not. So that's just what you see here. Okay, that's why they bother with these baseline characteristics. Okay, so it was a little different from your standard R labs, just reading a study or something. And if you guys come across research articles that are of interest that you think might be good for future classes, just let me know. I'm always looking for some good. Yes, Vicky. What was the answer to the last question? What was the last question? There is an important statistic missing from tables 2 and 3. Oh, that make it impossible. Okay, so basically we don't have the standard deviation or the standard error. Okay, so if you had the standard deviation, you could get the standard error. You need one or the other to figure this out. Okay, so we have the mean values, but we don't have S. Okay. I think I have to disable. Sorry. actually makes a big difference. Okay. Any other questions? We're good? Okay, so let me just talk about the class. So today I'm going to cover Anova, and next week I'm going to cover linear regression. And then next week, Saturday, will be a review. And then the week after that will be the final exam. So you have a quiz next week, and we'll go over linear regression. And then you'll have the final exam the week after that. Is that what I said? Yeah. So next week is linear regression. Week after is the final exam. The Saturday in between, there will be a review. Okay. So next week, and I'll say it again next week, is we will learn linear regression. There will be linear regression on the final, but the homework will not be collected for next week. Okay, so I'll take homework next week, but I'm not going to collect homework on the day of the final. Okay, so let's talk about Anova. Okay, so this is chapter 11. We're going to cover Anova. And so Anova allows us to compare the means from multiple groups. Okay. Contrast this to a t-test. Okay. A t-test allows you to compare means, but only when you have two groups. Okay. Okay, so you're comparing, mu1 versus mu2. Anova allows us to compare mu1 versus mu2 versus mu3 and more. Okay. And technically, Anova allows us to do more than that, okay? But what we're learning in this class is going to be just one-way Anova. Okay? One-way Anova is the simplest form of Anova, okay? And that's what we're going to learn. If depending on, I guess, your future research paths and things like that, if you are interested in taking another statistics course, I think a good next class to take would be one on Anova. It probably goes the title of the course will probably be Design of Experiments and Anova, or something along that line. Okay, they go hand in hand. Anova and Design of Experiments. I think that's a good next class. Unfortunately, nothing like that's offered through UCLA Extension. I would love to teach something like that, but not available through UCLA Extension. So, but Anova. So anyway, there's more advanced, or not advanced, but just more complicated forms of Anova, which I'll briefly mention at the end of today's lecture. But we're just going to learn one way of Anova today. Okay. So Anova stands for analysis of variance. Okay, so they take the AN and the O and the V, A for ANOVA, analysis of variance. And essentially what we're doing is you have all of your observations. If you were to throw all of your observations in one pool, okay, observations or measurements in one pool, quote unquote, okay, you will observe variance between the measurements. Okay, and in the beginning, so when they're all just in the pool, and you're saying, okay, well, we're seeing variance here. At this point, all you can say is, well, everybody's different, and that's why we're seeing different measurements. Okay, no two subjects, no two things are exactly alike. That's why we see different things. Okay, you have a bunch of cats and you're measuring their weight. Well, every cat is different, and that's why we see cats of different weight. That's that, okay? But then what we call it analysis of variance because we introduce a variable or a grouping. We introduce a grouping variable. Okay. And we look at the observations within each group. We introduce a grouping variable. Okay, so maybe you have a bunch of cats, and then you have you decide to split up the cats into different groups. I don't know, how do you split up cats? Maybe you put well, we'll just, in this example, there will only just be two. Maybe we have male cats and female cats, okay? And I don't know if there's a difference between male cats and female cats in terms of their weight. But we introduce a grouping variable, okay? And we measure the average for each of the groups, and maybe we see a difference. Maybe the average weight of a male cat is, some value, and the average weight of the female cats, okay, that we have observations for, is slightly different. Okay, and so what we want to do is we want to break apart this total variance that we see. We want to break it into two parts. We want to say part of the variance, part of the reason why we see different values is because the observations are in different groups, and then the other reason why we see different values is because individuals are different. Okay, so maybe someone will say, well, male cats are different from female cats, so that explains part of the difference. But even among male cats, you have differences between males, and even between female cats, you've got differences between females. So we're trying to break apart the total variance with everybody pooled together. We're trying to break that variance into different components. We've got variance because the groups are different, and then we just have variance that's because individuals are different. Okay. So into different parts. And so with Way Anova, it's just variance because the groups are different. Variance, that didn't sound right. Because the groups are different. And variance because is not the right word, but it'll work. Individuals are different. So no matter where you are, no matter what ANOVA study you have, you will always have variance because individuals are different. You can that is something that you can't get rid of. Everybody is different. And we have that, okay? So actually, maybe instead of cats, human height would have been a better example. You know, if we look at the entire classroom or entire group of people, everybody's a different height, okay? Well, maybe some people have the same height, but pretty much we see a bunch of variance between the heights of people. And then we could split the group into males and females, and we can say, well, part of the reason why you see different heights is because on average, males are taller than females, so part of the difference in heights is because of gender. Okay? But even if you look at all the males aren't the same height, and all the females aren't the same height. So even among that, you've got variance because the groups are different, and variance because individuals are different. That's what we're trying to do with ANOVA. Let me save this. All right, so let's start this off with an example. Okay, or actually, yeah. Okay, so let me just, I forgot. There might be an aside. So I said in the previous page, I said ANOVA allows us to compare the means from multiple groups, whereas a t-test allows you to compare the means, but only for 2 groups, okay? So if you have, let's say you have 3 groups, okay? So maybe it's not males and females, but you've got 3 different groups. So you so you observe, you know, y bar 1, y bar 2, and y bar 3, and these come from their respective populations. Population 1 with mu1, oops, and then pop 2 with mu2, and population 3 with mu3. Okay. Okay. If you only just had population 1 and population 2, you know, a t-test, you would have the null hypothesis that mu1 is equal to mu2 versus that it's not. Okay. With three groups, you would need to run multiple tests. You'd have to do another test where you've got mu1 equal to mu3, and then another test where mu2 is equal to mu3. Okay. So this is one option. One option is to run multiple tests. Okay. But there's a problem with running multiple tests. Okay. And it's not that we have to do a bunch of tests, because doing a bunch of tests, as tedious as it is, it's not the worst thing in the world, and with a computer, it's not that difficult, okay? So even if we were to have y bar 4 and y bar 5, you know, the number of tests you'd have to do grows geometrically, okay? So with the 4th one, you would have to do 6 tests, and with the 5th one, you'd have to do 24 tests or something like that, okay? The number of tests you'd have to run grows. The problem is not that you just have to do a bunch of tests. So if you had, you know, mu4, you'd have to do also mu1 versus mu4, mu2 versus mu4, and mu3 versus mu4. And then with 5, not 24, you jump up to 10 or something, okay? And with mu5, you'd have more things to do, okay? So the problem is our rate of type 1 error. Okay, the primary problem is rate of type 1 error, or I guess the biggest problem. So what is a type 1 error? Yeah, so type 1 error, once again, is the null hypothesis is true, but we choose to reject it. Okay, so mistakenly rejecting the null hypothesis. Yeah, and so the probability of type 1 error is equal to alpha. So if you say alpha is, let's 0.05, the probability that we commit a type 1 error when we do this hypothesis test is 5%. Okay, and then the probability that we commit a type 1 error when we do this test is 5%. And the probability that we commit a type 1 error when we do this test is 5%. Okay, and so the question is, how many tests can you run and emerge, quote, unscathed? Okay, every time you run a test, there's technically a 5% chance that you will commit a type 1 error. Okay, and if you don't want to commit that, how many tests can you run safely? And the answer is, well, if you're going to do a whole bunch of tests, there's a good chance that somewhere along the way, whether you like it or not, you might have made a type 1 error. Okay, so if you run multiple tests, okay, you run the risk. I mean, the risk is always there, risk of committing a type 1 error, but it grows quite a bit when you have many tests to do. Okay, so technically, so if I said if you did 6 tests, what's the probability of not committing type 1 error after 6 tests? What would you say? So if we could treat them as independent, okay, so if we have 6 tests, what is the probability of not committing type 1 error? Okay, so on one test, it's just 95%, right? You have alpha is 5%. So on 6 tests, we would say, well, maybe the first test had a probability of 0.95, and then the next test we have a probability of 0.95, so on and so forth for 6 times. So you got 0.95 raised to the 6, and this number is not, it's not promising, okay? 0.95 times, oops, 73%, okay? So you have basically an alpha of like 26%, 27%-ish, okay? Technically, it's not that. So the alpha for all 6 tests is close to, 0.265. That seems pretty significant, okay? It's technically not this because this calculation 0.95 to the 6th assumes all the tests are independent, and because you're using the same data in multiple tests, they're not independent, but you get the idea, right? That when you're doing a whole bunch of tests, we cannot ignore the probability of committing a type 1 error. Okay, it grows. So this is called the problem of multiple comparisons, and we don't have a very good solution. Okay, there's when you have multiple comparisons, there's some advantages to this. Okay, there's advantages to doing these pairwise test comparisons that are actually good. But so Anova is maybe one solution to it. It's not a perfect solution, but it allows us to do multiple comparisons without having to do multiple tests. We just do one test to see if there's a difference. And so the overall alpha is only 0.05 for that one test. But it's not perfect, and I'll explain what I mean here. Okay. So does this make sense? Problem of multiple comparisons. It's a long-standing problem in statistics. We don't have a good solution. Okay. If you can solve the problem of multiple comparisons, I don't think it's possible. I think that's just life. Okay. So anyway, let's talk about Anova, and specifically one-way Anova. Okay. So in Anova, your null hypothesis, if you have more than two groups, your null hypothesis is going to be along the lines of mu1 is equal to mu2 is equal to mu3. Okay? And the alternative equal to, however many different groups you have, you're going to have them all listed here. Okay? So the null hypothesis is that all means are equal. All group means are equal. The alternative is at least one of the mu's is different. Okay. And so inherently, whenever you have more than two groups, you can only have non-directional alternatives. Okay. Okay, because when we say at least one is different, we're not stating which one is different and whether it's bigger or smaller than the other groups. All we can say is just at least one of them is different. Okay. Let me just also, there's an alternate formulation of the hypotheses. Okay, because this formulation works only for one-way Anova. This alternate formulation allows the expansion of one-way into two-way Anova, or blocked Anova, things like that. Okay. So in the alternate formulation, we say each group mean is equal to mu, which is the grand mean of everything, plus what we call tau. Okay, so this mu is the grand mean of everything that we could possibly be interested in, and then tau is the quote effect, and I guess I should write tau sub I, the effect of being, or is it J? What letter do they use? I think I. Okay, the effect of being in group I, okay, is equal to mu sub I. So this is the alternate formulation. We're basically saying this would be an example. The grand mean height of everyone, average height, okay, of everyone, maybe we'll say is 67 inches, okay? And we'll say tau, if you are male, your group mean is 70 inches. So the effect of being male adds 3 inches to the mu, okay? Male, quote, effect. And then the effect, if you are in the female group, will be minus 3, okay? So that my mu's and my m's look the same. Okay, so the effect of being in the male group adds 3 to the mean, so your group mean is 70, and then the effect of being in the female group maybe is minus 3, so the mean of the female group is 64. Okay? Yes, question?
What if it was something like a category with 3 different categories? How would you
Yeah, well, I mean, so if there's like another category, okay.
Would it still be like positive, negative?
No. This is just, in this example, it's 3 and minus 3, but it's not necessarily plus and minus. It could be the effect is, plus 2 versus plus 8 versus minus something. There's always going to be at least one of them will at least be a minus and one will be at least be a positive, okay? But if you have 10 groups, maybe just one of them is minus and the other 9 are positive, okay? Probably not. It's probably going to be like there's going to be a split, but at least you'll have at least one minus and we'll have at least one plus in the terms of the effects, okay? So anyway, this is the alternate formulation would then be, if you're using this form, is that tau 1 is equal to tau 2 equal to tau 3, or however many groups you have, et cetera, are all equal to 0. Okay, meaning that being in a group has no effect on the average. And then the alternative is at least 1 tau is not equal to 0. You have a question?
Those be pluses or all equal signs?
They're all equal signs. They're all equal signs. Okay. Yeah. So this one is saying, yeah, everything is equal to 0. The effect of being in a group is basically nothing. Okay. This would be like, what's the effect of taking placebo versus St. John's wort? Okay. The effect in terms is there's an overall effect of, decreasing hyperactivity, inattentiveness, or something. There's an overall effect there, but is there an effect of being in this specific group versus this specific group? The study revealed no. There's no effect of being in this specific group or that specific group. Being in the study overall does have an effect, but that's going to be in the grand mean. All right, is that okay? The setup of the hypotheses for ANOVA. Yes?
So does that mean for HA being in a group does have an effect on the average?
I'm sorry?
For HA, does that mean that being in a group does?
Yes, so the alternative says at least one of the groups is different, so basically being in a group accounts for some of the difference in the variance, okay? So again, we're trying to break out the variance into two parts. Individual differences or individual variance, and then variance due to being in different groups, okay? And basically, the null hypothesis and all of these things are saying that being in different groups doesn't affect the variance, okay? It's just everyone's different, and that's that. That's the only source of variance that you see, okay? The alternative says okay, yes, everybody is different, but the groups also make a difference. Okay. So, if we looked at height, people can say, oh, everyone's different height. But then you'd say, yeah, well, yes, everybody is a different height, but part of the reason why they're different heights is because in general, men are taller than women. Okay, so gender accounts for something that makes a difference in height. Okay, why? There's who knows why, but that's actually because across the animal kingdom, it's it's different. It's different, huh? Like like male lions are bigger than female lions. Why? I don't know. Okay, but then if you look at spiders, female spiders are much bigger than male spiders in general, and things like what, why? Who knows? Okay. So anyway, that's that. But if you looked at something like intelligence, at least in the United States, measurable intelligence in terms of like SATs or IQ scores or whatever, you'll say everyone's different, okay, and then someone will say, well, is part of that difference due to gender or something? And if you do the study, you'll see, well, no, gender doesn't really make a difference in terms of your intelligence score, okay? It's just the best explanation we have is everybody's different, okay? But maybe if you introduced something like socioeconomic status and education attained and things like that, those might have an effect. And the effects of those might, well, I don't know exactly what they are. Okay, so let's work through one. We'll do Anova by hand with an example here. Okay. Let me find the data that I want to use. Okay, so we've got lamb diet data. So what we did was we took we have 12 different lambs, and we put them on 3 different diets. Diet 1, for lack of better names, we call them Diet 1, Diet 2, and Diet 3. And these were and we measured how much weight the different lambs gained. So we have 8, 16, 9. This is table in the textbook. It's available. Table 11 to 1. Okay. I have 9, 16, 21, 11, and 18. In Diet 3, we have 15, 10, 17, and 6. Okay. So for each of these, we have a group sample size. So this is n sub I, saying so the size of sample 1 was 3. We have 5 measurements here, 4 measurements here. And we can take the average of 8, 16, and 9, and the average is 11. The average of these 5 numbers is 15, and the average of these 5 numbers, or of these 4 numbers, is 12. And we can get the standard deviation, and the standard deviation is 4.359 for this group. For this group, it's 4.950. And for this group, the standard deviation is 4.967. Okay, so let me graph this here. Let's see. So let's start off here at 6, 7, 8, 9, 10. There's probably a tool in here that can do a better job at this. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 and 21. Okay, so let's see. Let's go to, I'm going to call this diet 1. I'm going to make a dot plot, diet 2 and diet 3. Okay, so let's see. Diet 1, we're up at, let me just use a pencil here. Stop with the sticky keys. Okay, so diet 1, we're at 8, 16, and 9. And then diet 2, we're at 9, 16, 21, 11, and 18. And under diet 3, we're at 15, 10, 17, and 6. Okay? Is that all right? Okay, so we see overall we've got variance, okay? And let me just create kind of a pool. So if I throw everybody into the pool, the same one, we'll see, this is what we'll see. Okay? And so we see, okay, the different lambs, they gain different amounts of weight. And so we want to say, well, did they gain different amounts of weight because they were on different diets? Or did they gain different amounts of weight because all the lambs are different? Okay. Well, I mean, the individual differences will always be there. Okay, but we want to know, do the different diets have an effect in terms of how much weight is gained? Okay. So we're going to calculate something called the grand mean. Okay. The grand mean of our data, okay, we're going to label y double bar, okay? And this is equal, this is not, it's not the mean of 11, 15, and 12, okay? It's the grand mean of if we took all of these data points, so we do all 12 data points, the sum of all 12 data points divided by 12, okay? Now, if you had a giant data set, you don't want to have to add up 300 numbers, okay? So a little shortcut to get that, to get the sum of all 12 data points, is you would do n times y bar for each group, divided by the sum of the n's. Okay. So in that case, I would do 3 times 11 plus 5 times 15. So this is kind of a shortcut to get the sum of all 12 numbers, divided by the sum of 3 plus 5 plus 4. And I get 156 over 12. I get a grand mean of 13. Is that okay? So I want to indicate that maybe with right here. Okay, so I'm gonna draw a blue line. This is our grand mean here. Y double bar. Okay. Now, do you remember the definition of variance? Or the square standard deviation, because the standard deviation is the square root of the variance. So do you remember what variance? How do we get variance? where it's the kind of the average squared distance from the mean. Do you remember that? It's like the quote-unquote average or typical squared distance from the mean. So we would take each data point y and we would subtract off the mean, we would square them, and then we would take the average. So we would add them up and then we would divide by not n but n minus 1. Okay, that would be our variance, s squared, the variance. This looks familiar? Okay, good. Okay, we have the idea of kind of like the total variance of all of these, if you think about that. Of all the data would be y minus y double bar squared added up over n minus 1. Okay, so essentially what we would be doing is we would look at each data point and we would say, oh, well, this data point is right here, and that's this far, so this is the distance y minus y double bar, and we're squaring it, okay? And we're doing that for all of these data points right here. This one is right there, and we do y minus y double bar, and we square it, and we do it for all the different data points, okay? And we add them up. We would get a total variance for all of these points of data. But what we want to do is we want to break down this total variance into two parts. Part of it is due to the different groups. Part of it is due to individual differences. Okay, so let me make a new slide. And let me just crop out, chop away this stuff. Okay, so let's do that. Okay, so if I look at group 1, the average of group 1 is 11. Okay, and if I look at group 2, the average of group 2 is 15. And if I look at group 3, the average of group 3 is 12. Okay. So what we're saying is that, you know, this data point right here, this one, the amount it differs from the grand mean is this much, okay? But we're going to break that distance from the mean into two parts. We're going to say, okay, well, it's actually this point's group is this much different from the grand mean, and this individual point is this different from the group mean itself. Okay, so we're breaking up the basically this deviation, the total distance from the mean, we're breaking it into two parts. Part of it is because the group itself is different from the mean, and the other part is that this individual data point is different from its own group mean. Okay, so we break apart y minus y double bar into two parts. Y, the group mean, and the individual from its group mean. So this is group difference from y double bar, and this is individual difference from its group mean. Okay, so that's what we're aiming to do. Let's see. Let me save that. And let me, how do I want to do this? Okay, so I'm going to copy everything again, make a new slide, and I'm going to chop out the graph this time. Okay, so we're going to create an Anova table. And we do this, we have what we call the source of variance, and we have the between groups and within group. Let me actually give myself more space here. Okay, for total variance. Okay, so the Anova table will have a column for degrees of freedom, which I'll get to in a moment here. Okay, but the key thing, the next part is we're going to deal with the sum of squares. Okay, so when we calculated variance, we said everything is, y minus y double bar squared and divided, add them up, divide by n minus 1. Here we're going to just get rid of that denominator, and we're just going to look at that top part, the sum of the squares. Okay, so the total variance would be, we're taking each individual data point and we're subtracting off the grand mean, and we square them, and we're adding them up for all the different data points. Okay. All right. But we're going to do this, we're going to break that apart into between groups and within groups. Okay? So between the groups, the sum of squares is going to be y bar minus y double bar squared. Okay? We're going to do that, but then we have to do it for every single data point. Okay? So the first group has 3 data points, okay? And the second group has 5, and the third group has 4. So we're going to take this difference and multiply it by how many data points are in that group. And then we add them up. So let me just save that. So I'll let you guys write that down. So just on the previous slide, we have this difference, right? This is y bar, and this is y double bar. So we're taking this difference from here to here, and we're squaring that difference, but we have to do it 3 times. And then we're taking this difference right here, we square it, and we have to do it 5 times for the 5 data points here. And we do this difference, and we do it for the 4 data points here. Okay. Okay, so that's going to be the between group sum of squares. Okay. The within group sum of squares is just going to be y minus y bar squared for all the data points within a group, and then we do it for all groups. Okay, so we do it, there's 2 sums here because you do y minus y bar for all the data points in one group, and then you have to do it for all 3 groups. Okay, so for each group, or for each point in a group, and then this one is for all groups. Is that okay with everyone? Does this make sense? No? So, yeah, we'll do an example, okay? All right, so we'll look at this, we'll look at these first three data points here, okay? So, if we look at the total variance here for these first three data points, the grand mean was, what was it, 13? Okay. The grand mean is equal to 13. Okay. So if we looked at the total variance just for these first three data points, we would do 8 minus 13 squared plus 16 minus 13 squared plus 9 minus 13 squared. Okay. So on and so forth. These are the differences from the grand mean for each of these three data points. Okay. We're going to break apart this variance into part of it due to the group being different, okay? And so if we look at this group mean, the group mean is 11. So we're going to say 11 minus 13, and I'm going to square that difference. And I have three data points, so really the first data point, its group mean is 11 minus 13 squared, okay? The second data point is also 11 minus 13 squared, and the third data point is also 11 minus 13 squared. So I'm just going to multiply that by 3. Okay, and I would have to do this for all three data groups. Okay, dot, 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 dot. Okay. And if I look at the variance within a group, now I'm seeing, well, 8 is different from 11, and 16 is different from 11, and 9 is different from 11. Okay, so I would say, I would do 8 minus 11 squared plus 16 minus 11 squared plus 9 minus 11 squared. Okay, and I would have to do the same for all three groups. Is that okay? So we have a shortcut, okay? Because, we want to try to avoid doing too many tedious calculations when we can, okay? And to do the within group calculations would require us to know each individual data point, and we would have to do, 8 minus 11 squared. We'd have to do this for every single data point, and we would like to avoid that if we can, okay? So we have a shortcut for the within group, okay? So within group, the shorthand is sum of squares within, okay? We have a shortcut. So this is defined as, y minus y bar squared for all the points in a group, and we do it for all data points, okay? Let's just recall definition of variance. S squared is equal, we said, y minus y bar squared over n minus 1, right? This is the definition of variance, okay? Well, lo and behold, y minus y bar squared summed up, we see that right here, okay? So if I multiply both sides by n minus 1, n minus 1 times s squared is equal to y minus y bar quantity squared. So I'm going to just plug this in right here, and so sum of squares within is n minus 1 squared. I'm sorry, not n minus 1 squared. It's n minus 1 times s squared for each group. Is that good?
You say N instead of
N is each group's, yeah, Ni, yeah. Right here. Okay. So, so we can kind of do this. So for this one, so for diet 1, you know, our first one is going to be 3 minus 1 times s squared, 4.359 squared, okay? And we'd have to do it for all 3 groups. And these numbers should all match. They should add up. So the between group sum of squares and the within group sum of squares, these should all add. Okay? So if I do 11 minus 13, that's 2. 2 squared is 4 times 3. So I have 12 over here. 8 minus 11 squared is 3 squared, or 9, plus 16 minus 11, 25, plus 9 minus 11 is 4. So that is, I can't add for some reason, 34, 38. Okay, and over here, 8 minus 13 is 5 squared. 16 minus 13 is 3 squared, so 9. And 9 minus 13 is 416. And please, I hope this adds up to 38, otherwise I can't add in my head. Does it add up to 38? No? Oh, well, we have to do it for all 3 groups. That's our problem. Yeah. Oh, yeah, this adds up to 50. Okay. Okay, but I promise if... Oh, no. We're okay. It doesn't add up to 38. 12 plus 38 adds up to 50. Yeah. We're okay. Because between group, the 12 plus the 38. So we've broken out the total variance of 50 into this component of 38 and 12. So 12 is due to the fact that this group is different from the grand mean, and then 38 of it is due to the fact that the individuals are just different within the group.
And what does it represent again? The 9, the 25,
Oh, this is the 8 minus 11 squared is 9, and 16 minus 11 squared is 25, and 9 minus 11 squared is 4. Okay, so we're breaking apart the variance into individual components here. So the picture for this is, this is the difference from the grand mean, and we're breaking it into 2 parts. Part of it's because the group mean is different, and the other part is because the individuals are different. So that's what Anova is. We're breaking apart the total variance into, I don't know, different aspects. Okay, and if we did, we used the shortcut to get 3 minus 1 times 4.359 squared, that should be 38, I hope. 4.359 squared times 2, 38. It's a little off because of rounding, but yes, this is equal to 38. And we do that for all the groups, all the data points, and we get the total variance for everything and whatnot. If you're confused, feel free to stop me, and I'll try to clarify things. Yes?
Where did you get the 3 times 4 from?
Oh, I'm sorry. This is right here. 11 minus 13 is 2, or negative 2, and I square that, and I get 4. Okay, and then I multiply that by 3. I'm just doing the arithmetic for each of these formulas here. Okay?
3 is the n?
Yeah, 3 is the n. The n is the group n here. Okay? Okay, so that is getting our sum of squares. Okay, so let me so our complete Anova table has our source, between groups, within groups. Okay. We have degrees of freedom, sum of squares. Let me do total here. And we have what we call mean squares, and we have the F ratio. Okay. So sum of squares, we just covered those. That's going to be n times y bar minus y double bar squared. So the group mean difference from the grand mean difference. And within the groups, I'm just going to put the shortcut n minus 1 times s squared. Okay, total sum of squares, y minus y double bar, summed up for all points. Okay. But because this and this add up to this, you don't actually have to do this, all right? Okay, degrees of freedom. I'm going to just do shorthand. N dot is going to be number of all points. To distinguish from the n sub i's, n of each group. So if you add up all the group n's, so in our case we have a total of 12 with our lamb data. Okay, so our degrees of freedom here is n dot minus 1. Okay. Between the groups, degrees of freedom is the number of groups minus 1, and these two things add up, so you have n dot minus I, so that you get n minus 1. So this is number of groups minus 1. Maybe I'll just caption that so you can remember. Number of groups minus 1. And this is number of points total minus 1. And this is this minus this. It's basically everything has to add up. So this plus this must add up. So it's whatever you need. So it adds. I know, it feels a lot of formula heavy. It feels formula heavy, but the main concept is we're breaking apart the variance. Okay, and if you can remember what variance is, it's or if you just think of the squared distance from the mean, and you're trying to break it into the different components, part of the difference is part of that distance is because the group is different from the grand mean, and then the other part is the individual difference. I think you can help keep all of this straight. Okay. The mean squares, we have this thing called mean squares, and basically you just do the sum of squares divided by degrees of freedom, and you do this for both. Okay. We don't bother with the total, mean squares total. We don't do that. You just take the sum of squares and you divide by the degrees of freedom, and the F ratio exists for any source that's not within. So in this case, it's just the between. It's going to be the mean squares value, mean squares between, divided by mean squares within. All right, so let me just copy the data table from. I'm sorry?
The F ratio is just a combination of the two.
Yeah, but we only have F ratio for the top row. Okay, so let me just copy this. Okay, so we'll make the Anova table right here for this data. Okay. So we have source, and I'm going to do between, within, and we have degrees of freedom. Okay, so degrees of freedom, we have 3 groups. So our between degrees of freedom between is going to be 3 minus 1. I've got 2 right here. The total degrees of freedom, I have a total of 12 points, so I'm going to have a total of 11 degrees of freedom. Okay, and then so you just say 2 plus what adds up to 11? 9. Okay, or you can use this and do, there's a total of 12 points minus 3 groups. I've got 9 degrees of freedom here. Okay, we're going to do the sum of squares. Okay, sum of squares is n times y bar minus y double bar quantity squared. Okay, so if I do this for all 3 groups, okay, I'm going to have 3 times 11 minus 13 squared plus the next one is going to be, I have 5 data points and the difference between that is going to be 15 minus the grand mean of 13 squared. And then the last one, I've got 4 data points, and it's going to be 12 minus 13 squared. Okay, so if I do this, I have, I think 12 plus 20 plus 4, and I have 36. Is that okay? We're just using these numbers right here. Maybe I'll use a different color for the last one, okay? And then over here, I'm going to do n minus 1. So 3 minus 1, so 2 times s squared, 4.359 squared, plus the next one, n minus 1, so I'll do 5 minus 1, times 4.950 squared, and then the last one will be 4 minus 1 times 4.967 squared. And that number, let's do that. We just did that one, so we do 4 times 4.95 squared plus, oops, no, how do I get out of here? Plus 3 times 4.967 squared. Enter. 210. Okay. The numbers are a little off because of the rounding of the decimals in this. Okay. All right. So the total sum of squares, we don't even have to bother doing the individual calculations. We could if we wanted to, but they always add up. 246. Okay. The mean squares is going to be 36 divided by 2. Sum of squares divided by degrees of freedom, so I have 18 right here. And then mean squares within is going to be 210 divided by 9. That's not helpful. Two 10 over 9, 23.33. Is that okay? And so my F ratio is going to be 18 over 23.33. I get an F ratio of 0.7714. Okay. Creation of the Anova table, okay. Yeah?
So the total MS would be good.
There's no total MS. We don't, I mean, I guess you could do 246 divided by 11, but we just don't do that. I don't know. we don't bother with total MS. Okay? You have MS between, you have MS within, you have sum of squares between, sum of squares within, and degrees of freedom and all of that. And the F ratio only just does not exist for the last row. In other forms of ANOVA, you have other sources, and you'll have an F ratio for each of those, but it doesn't exist for the last one. Okay. Is making this okay? Feels okay? All right. So let me just explain the F ratio, okay? Because this is where we do our hypothesis test. So actually, let's go back. Let me just copy this. Okay, so if we recall what our hypothesis was mu1 is equal to mu2 equal to mu3, or we could have also written tau1 equal to tau2 equal to tau3, which is equal to 0. Okay, we can say either all the group means are the same, or that the effect of being in a group is nothing. Okay, either of those are fine. And the alternative is at least one group mean is different. Or we could write at least one tau is not equal to 0. Again, these are non-directional because we have more than two groups. If you have two groups, that's the only time you can have a directional alternative for this. But if you only have two groups, you might as well just do a t-test. I think it's a little easier. I think they end up being equivalent at their, what they call asymptotically equivalent, but that doesn't matter. Okay, so what we're going to do is we're going to look up the F ratio in the F table, okay? Now, if you're curious where this F table comes from, it's the result of, it doesn't matter, ratio of t distributions. And it's F because the guy Fisher was the one who came up with it. But anyway, the thing about the F table is that there are 2 degrees of freedom to look up, okay? You have the numerator degrees of freedom and denominator degrees of freedom. Okay, you have 2 degrees of freedom to look up. And so in our case, our numerator is going to have 2 degrees of freedom, and our denominator is going to have 9 degrees of freedom. Okay. And so the F table is not one of your reference tables that I have handed out to you, okay? And actually I don't even have a table to project up on the screen. But there is a different page for every single numerator degrees of freedom up through like 10 or something, okay? So there's 10 pages of the F table. You have, the first one is numerator degrees of freedom 1, you get numerator DF2, numerator DF3, numerator DF4, all the way up to numerator DF10. So you've got a bunch of pages of the F table, which is why I didn't bother giving it to you guys. And so anyway, when you look up the F table, it works very similar to using the chi-squared table or the T table, okay? Basically but it just has the additional step of figuring out your numerator degrees of freedom, okay? So basically you go to the page with numerator DF. It looks, at that point, it looks almost just like a chi-squared table, and you just figure out your degrees of freedom for the row, and then you look up your test statistic to get your tail probability. Okay, and that's it. So anyway, if we were to do this in our case, we would use numerator degrees of freedom 2, and we would go to the row, okay, where it says DF. We would go to the row 9 degrees of freedom, and the tail probabilities, the first one is 0.20, and then they get smaller. It's just like using a chi-squared table. I have 1.93, 3.11, etc., etc., etc. Okay. So if my F ratio is 0.7714, what would we say about my tail probability? Tail is greater than 20%. Okay. And with the F table, your tail is just going to be your p-value. So our p-value for this hypothesis test is over 20%. Okay. So in terms of next week's quiz, there will be a section on Anova. I will not have you guys look up numbers in the F table, okay? I might ask you what would the degrees of freedom be that you would use, but I figure if you know how to use the chi-squared table, you know how to use the F table, okay? So there's no worries there, okay? And save us some paper. We don't have to print out 10 pages for everybody. All right, so if our p-value is over 20%, what is our conclusion? Okay, conclusion is do not reject the null hypothesis. And what does that mean? In the context of our problem, that means what? Yeah, the different we don't have any evidence suggesting that the diets make any difference. Okay, I mean, or we don't have enough evidence, I should say, because we only looked at 12 lambs. Okay, so we don't have evidence to say that the different diets have different mean weight gains. Okay. What is the meaning of this p-value? P-value greater than 20%. What does it mean? So the p-value is our probability of observing our data if the null hypothesis is true, right? Our data, or something more extreme, so in this case, it would be, what is the probability if we look at our data what's the probability I would get 3 groups of lambs where the mean weights are this different, okay, if the means of the populations were actually equal? Okay, so we would say, if mu1 equals mu2 equals mu3, then there is still over a 20% probability that a random sample of 12 lambs would show basically these different weight gains, different group weight gains. Okay, why don't we take a break right here, and we'll come back and I'll talk a little bit more about the other forms of ANOVA. I'll just do a quick demo on the computer, and we'll call it an evening there.